All right, this is going to be a pretty short lecture. This is information that I expect most of you probably have pretty good knowledge of, but I still like to review it because some students haven't maybe reviewed it in a few years, and it's just nice to kind of review scientific notation and units of measurement. First of all, with scientific notation, the purpose of it is to try to write a number, a very large, very small number, in a manageable fashion. So when we see this first number here, 3,260,000, to put in scientific notation, first of all, the decimal point is at the end of the number always that you write, okay? Or it's at the start of the number if the number is less than 1. Now that decimal point, we want to move that decimal point so that the final number in scientific notation is between 1 and 10. So it's got to be bigger than 1, but it's got to be less than 10. It can be equal to 1, but it can never be equal to 10. Okay, so ideally, unless the number is a whole number with 1 in front of it, the number should be a value that's between 1 and 10. So I want to move the decimal point 1, 2, 3, 4, 5, 6. Once I move it 6 places, there's only one number to the left of the decimal point, and that's typically where we want to put it to bid in scientific notation. So now instead of being 3,260,000 with the decimal point at the end, we have the decimal point now between the 3 and the 2. So it's 3.26. Because we move the decimal point 6 times to the left, that'd be 10 to the 6. So in scientific notation, it's 3.26 times 10 to the 6th. One little thing to remember is the most common mistake students make is on the power. Most often they put it, if it's wrong, at -6. And that's probably because when you move left or right, it depends, are we going into scientific notation or auto notation to determine what the size of the number is. I always say use common sense. If the number is bigger than 1, 3 million, much bigger than 1. If it's bigger than 1, okay, then we are going to want to have a power that's going to be a positive number, okay? If it's less than 1, then it's going to have a negative power, all right? Okay, same thing here with the number. A lot of times when the number is much smaller than 1, they'll be kind of written out in groups of 3 to make it easier to count. But here again, I want to move the decimal point 1, 2, 3, 4, 5. If I were to stop it here, I still do not have a non-zero to the left of the decimal point. So I need to move it one more time. And now when I stop there, I would have 1.540. There's one number to the left of the decimal point, and now you'll notice that 1.54 is between 1 and 10. The number 1.54 is between 1 and 10. So I'm good there. And since I moved it 6 to the right, now it's -6. This is a number that is less than 1. If it's less than 1, our power should be a negative quantity. Okay? There's a question here. You'll notice that when I wrote the number 1.540, that I did not include the first set of zeros, but I did include the very last zero. Why does that need to be included in the value? And the reason why is that 0 at the end tells me where I measured the number to. It gives me a level of precision. And that's very important in measurement taking in science. So if I have a number that's 3 and a number that's 3.0, believe it or not, those two numbers are different. 3 tells me that I measured to the ones position. 3.0 tells me I measured to the tens. And with precision of instrumentation, the more precise a measurement is, the more and more money it is, because it's just that much more of a specific instrument. So there is a difference between numbers. So zeros at the end of the numbers are important because they give us an indication of the level of precision of it. All right, so that's scientific notation. Now, I didn't give you an example going the other way. So on the very bottom here, I'm going to give you a couple examples here. So 2.74 times 10 to the -3rd, and 4.58 times 10 to the, let's go 7th. Okay, if we're going the other direction, if it's -3, am I going to move right? No, if I go to the right, I'm going to get a number that's going to be much bigger than 1. Negative tells me the number has to be less than 1, and so I've got to have a decimal number. So I got to move it 1, 2, 3. So wherever the humps have no numbers, those will be 0. So this number in scientific notation will be 0.00274. And if you want to put a 0 in front of it, you can, but it's not necessary. 4.58, since the number is positive 7, we're going to move it 7 times. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5. So this number now is going to have 5 zeros after it. So when I'm done, I've got a number of 45,800,000. Okay? So just a way of, again, knowing how to do scientific notation. A metric system. In chemistry, we are always going to use the metric system. Okay? In the 1700s, there was a decision by the scientific community that we always measure numbers or measurement taking with a specific unit quantity. That way, someone in Poland, someone in England, someone in the United States, we're all measuring using the same system. And they decide on the metric system. Doesn't mean know why. And that's because when I move from centimeters to meters, for example, all I have to do is move the decimal point. Everything is a factor of 10. And because it's a factor of 10, when I want to convert between units of measurement, all I have to do is simply move the decimal point. I don't have to worry that I have to know that there are 16 cups in a gallon. Or then I would either have to multiply by 16 or divide by 16 to convert cups into gallons or gallons into cups. That's why the system we use in the United States, the customary system, is it's a lot harder to utilize. That's why metric was decided in the scientific community. All right. Not only, and we'll talk more about movement of the decimal place when we get into dimension analysis, which is down here. You'll notice that we use the metric system and have all these prefixes. I'm going to come back to this when we start talking about dimension analysis. For the sake of today's homework, it's going to mainly just focus on scientific notation and measurement taking. Okay, so in length, the scientific community agreed upon a specific measurement quantity to measure all lengths in. That was defined to be a meter. Okay, if you were abbreviating it, it would be just M. So meter, in an English unit, what's the closest English unit that we have that you're familiar with, hopefully, that is equivalent or pretty close to being, not equivalent, but being as close as possible to a meter? And hopefully you said a yard. Okay, about 3 feet is the length of a meter. Mass was determined to be a kilogram. Not a gram, but a kilogram. It's the only SI unit of measurement that is actually have a prefix attached to it. So kilogram is abbreviated kg. The closest unit of mass to a kilogram, okay, would be something called a slug, which we no longer really use. Not a pound, because a pound is looking at weight, not mass. Mass is the amount of matter in an object. Weight is the amount of mass times the gravity on an object. So weight is something that would involve your body with the gravitational pull of where we are currently, the Earth. Those two as being a product. Your mass is very different than what your weight is. If you go to outer space and you are effectively at 0 gravity, you have 0 weight. You're weightless, but you still have the same mass. Your kilogram mass is the same here, no matter where you are in the universe. Time is only measured in seconds, and that's true for both English and metric system, measured in seconds, which would be abbreviated as just simply S. Temperature, the metric system that we utilize, is Kelvin. Okay, we use Kelvin measurements in this class, not even Celsius. If you have a Celsius temperature, let's say 20 degrees Celsius, to convert Celsius into Kelvin, you add 273 and that will convert any Celsius temperature into Kelvin, simply at 273. Okay? Does anybody know the coldest temperature known to theoretically exist? It's called absolute zero. How cold is absolute zero? 0 Kelvin, 0 K. Okay, there are no negative numbers with Kelvin. It's all positive. And theoretically, we can't even achieve 0 K, 0 Kelvin, absolute zero. So the theoretically coldest temperature in Celsius then would be negative 273 degrees Celsius. That's as cold as anything theoretically could ever get. Okay? English, of course, we measure everything in Fahrenheit. Okay? Volume. Okay, how do we convert volume? What do we measure in? We measure things in liters in the metric system. Oh, Kelvin is just symbolized as a big K. No degrees K, it's just Kelvin. 25 Kelvin, 385 Kelvin, 1054 Kelvin. Okay, liters is given as a lowercase l. And the closest English unit of measurement to a liter would be a quart. A quart and a liter are fairly close to each other. So in this class, again, we're not going to be focusing about the English. We're going to take measurements utilizing metric always for the sake of this course. All right, so now what I'd like you to do is the next page in your packet, there are some practice problems in scientific notation. I'd like you to do those. I've supplied the answer key, so please complete that, take a look at the answers, and that'll be it for today when it comes to honors chemistry. Again, if you have any questions, please don't hesitate in contacting me. Thanks for listening.